Hi all, welcome to part 25, module 2, logic system design. See, in the last part what we were discussing is about the design of a logic circuit, right? So we already know about the basic gates, how things are working. So this is what we were discussing in the last class, the fundamental logic gates, that is about the AND gate, OR gate, NOT gate and their notation, truth table, everything you know, right? And how about the implementation of given logical operation? It's like first you come up with a Boolean expression that um, represents the logical meaning of what you want to perform, right? So come up with the Boolean expression of that, and then we will so the every Boolean expression there will be a corresponding truth table representations or the kind of mapping. And this truth table representation itself we are representing using something called a K-map, a more convenient representation from which you can directly go for simplification in a very easy way. So this K-map is nothing but another way of representing the truth table only, but from this simplification is something easier for you, right? And from that we will come up with the minimum expression, minimum Boolean expression, something like that, minimum SOP or POI, sum of product or product of some expressions, the standard notations, right? And why we have to minimize using KMAP? Because the original expression may be somewhat containing more number of literals and logical operators, and once you minimize it, you can implement it using some very small circuit, right? So by using minimum number of gates and all. So that about it. And typically, you know, in the product terms, if you are coming up with the minimum sum of product expression, the product terms can be implemented using the AND gate, right? Two input AND gate is typically what we have, but we can think of three input or some n input AND gate. Then final, these product terms are added together, right? So that is what is implemented using the OR gate. So a two level the AND OR realization can do this. And the first level, gates will implement all the product term. Now in the second level, I mean to the level after implementing all the product terms, you can go for the or term implementation. So that about it. So now in addition to this basic gates, we have some additional gates like XOR gate, XNOR gate, NAND, NOR and all, right? That also we saw in the last video, like how this XOR gate, what is this logical expression, the default implementation of it, but you know, using fundamental gates. But we have a small circuit, a small logical chip, typically denoted by this symbol, that can do the whole thing, right? So when you are giving two inputs, it will output the XOR of these two. So you can directly use it, or you can implement it using the AND or realization also. Now XNOR is something complemented of this XOR gate, that you know, and a NAND gate, the negation of AND and negation of OR gate. Now we introduced something called the universal gates, and we saw that the NAND gate and NOR gate, they are typically known to be universal gates. Means just using this NAND gate alone, you can implement any other gates or any complicated Boolean algebraic expression you can implement using just NAND gate alone. So that is the power of this gate, right? So that is what we are what we proved in the last video lecture, where we tried to implement not gate, the fundamental gates using the NAND. So once you can implement all the fundamental gates, that is AND, OR and NOT, you know, any other Boolean expression can be implemented just using this NAND gate, NOT gate and OR gate, right? So we already seen any expression you can represent using minimum SOP or minimum product of sum, that in turn will be represented by AND gate and OR gates. And sometimes to complement the literal, the variable, we can use the NOT gate also. So that is enough. So if we can implement these three gates using NAND, that means any Boolean expression you can implement using NAND gate. So that is the interpretation. So first we saw how this NOT gate can be implemented using NAND, you know. So you know, the NOT gate is just the inverter, right? So that will when you give an input to it, it will give the complement of it. Just if you are applying 1, it will give you 0's output, 0 like that. And to implement it using NAND gate, what you can do, NAND gate is typically a binary gate, 2 inputs are expected. Now both inputs you merge and you can apply for the single single input, because this NOT is a unary operation, right? So we can give only a single input to this NAND gate if you want to implement NOT gate. Now this NAND gate is going to give you a dot a, the whole complement, something like that. Now from idempotent law we have a dot a is nothing but a. Now a dot a, the whole complement, is a complement. So you are getting the complement, right, simply by merging two inputs of the NAND gate and applying the single input. So that will give you the negation of it. So that is fine. Similarly, the implementation of AND gate using NAND gate we saw, right, because single NAND gate is going to give you negation of the AND gate. So you can use one more an inverter further. That inverter is nothing but another NAND gate. So two NAND gate connected in serial like this can implement a AND gate. So that is also we seen. I think while we discussing this, I got some interruption in the last video lecture, so I am continuing from this point. So the implementation of the OR gate using the NAND gate. So that what we seen there is like so what you have to implement is the OR gate, right? So so before moving on to that, what we can see is the bubbled, the OR gate is nothing but the something like this. So you can see that so given an AND gate like this, if you are applying both of its input by taking some complement before, something like A and B. So at this point, this small circle indicates that some inversion is happening here. So output of, I mean, the actual input of this particular NAND gate is A complement, something like this. Similarly, here it is B complement. So the NAND gate is going to give you NAND of this, I mean AND and negation, that is A complement dot B complement. The whole complement will be the output of this NAND gate, and you know this is nothing but A complement by De Morgan's law, A complement the whole complement, and this dot become plus, and B complement the whole complement, and that is nothing but A plus B. So this is how, see, easily you can implement the OR gate. So the NAND gate only, but both inputs you applied by inverting them. Now the inverter itself we can implement using an NAND gate. How it is to be done? So you can use, instead of an inverter there, you use a single NAND gate. Now input A you can apply, so that this is going to give you this A complement. Similarly, use another NAND gate like this, and for this you can apply this B, so that this is going to give you this B complement as output. Now these two things you can apply together to the third NAND gate. So this is the third NAND gate we are having. Now in see, instead of this inverter and inverter, I used two NAND gates, that's all. So 3 NAND gates I need. So this is going to give you A dot the whole dot B dot the whole complement, I mean A complement dot B complement the whole complement, that is nothing but A plus B. So this is how you can implement the OR gate using NAND gate. So what is our conclusion? So what we seen is like we can implement a NOT gate using one NAND gate, and you saw its implementation, right? How to be so simply merge both of its input, that's all. And the AND gate can be implemented using two NAND gates, because the first NAND gate is going to give you the actual NAND, you have to negate it once again, that's all. And the OR gate is being implemented using 3 NAND gates. Now let me ask you, can you try in a similar way the implementation of the fundamental gates using so NOR gate? So that is let me give it as an exercise for you. So what you have to do in a similar way, like this is a university question, right? So you have to expect this implementation of the fundamental gates using NAND or NOR gate. They can ask, or they can ask you the question like prove that NAND gate is a universal gate. So you can prove like implementing all the fundamental gates. So both of them you can expect. Similarly, now the thing is that NOR gate is also universal gate. What I mean by universal gate means it can implement any Boolean expression. So it is powerful enough, right? It's something universal. So NOR gate, how can you prove it? First you have to implement the NOT gate using NOR gate. You can guess it now, right? So just like you can try it yourself. The NAND gate implementation use a single NOR gate, and means just do like that. You can see that one NOR gate is enough. And similarly, for the implementation of AND gate, see now can you tell me which will be easy for me to implement using NOR? Implementation of OR gate or AND gate? It will be OR gate, right? Because NOR gate is going to give you complementation of OR. So use one more NOR gate. So 2 NOR gates are going to give you, just like 2 NAND gates are going to give you an AND gate. Here no, 2 NOR gates, same way you can connect. NOR gates are going to give you a single, I mean the OR gate functionality. Similarly, the NAND gate implementation you may find it difficult. Just like the NOR gate implementation, 3 NOR gates can be used to implement. So just like the way you try, like what we done for NAND gate realization. So this will going to give you the AND gate, right? So that is a proof. that is why it is called as, because you can implement all the fundamental gates. So now what is the benefit of implementing all the fundamental gates? Also you can implement all the fundamental gate, you can implement any Boolean algebraic expression, because ultimately any expression is some SOP or product of some expression, right? So that you can do. Fine. So that about it. Now let's continue. So this is what we see. NAND gate is said to be universal gate because we can, so those theory concepts are there. So this is something I taken from the textbook. The inverter, they are using the inverter notation, but actually this is nothing but, this inverter is actually to be implemented using a NAND gate only, but in the textbook they are giving like that. So this is the correct way. And similarly for AND gate implementation, just like use one AND gate and use one more AND gate, and the second, that inversion part, they are using directly the NOT gate, but that is not the way, this is the way. Okay, similarly here also that inversion part, inversion they are handling separately, the inversion part is implement using an AND gate only. Okay, and you know this, right? So that about it. Similarly the NOR gate implementation. So this is something like the 2 input NAND gate is what we seen already, but here this is the 3 input NAND gate. Similarly n input NAND gate you can think of, and you can see that this 3 input NAND gate or n input NAND gate is equivalent to something like a bubbled, or I can call it as a, so this is a NAND gate, right? So this is 3 input NAND gate in general, and n input NAND gate is equivalent to same n input, it can be 1 input, 2 input, whatever it is, some it's equivalent to some n input bubbled OR gate, bubbled OR gate. So I am calling it like this, this is bubbling according to me. Okay, so that is bubbled OR gate is nothing but some invert OR, so some set of inversion is happening, then OR operation is happening. So this bubbled, I mean the inversion, right? Invert OR gate. Okay, so that about it. So you can see that this NAND gate is nothing but, whether it is 2 input NAND gate or n input NAND gate, this NAND gate is nothing but it is equivalent to, you can see that some AND operation, right? Actually we have an AND operation followed by an inversion, and after that bubbling, right? Something like that, AND invert. So that is further equivalent to, see, this is equivalent to this. Now this is further equivalent to use some set of inversion at the beginning, then OR, invert OR, that is nothing but bubbled OR. This bubbled OR is typically the usage. Yeah, that about it. Now that about it, yeah, one more topic is left, is like how to implement any Boolean function. So what we seen already is using NAND gate or NOR gate, you can implement any fundamental gate. In that way, right now it is very clear for you, like any complicated Boolean algebraic expression can be implemented just using NAND gate or alone or NOR gate alone. So that is what we see. Now can we do it in a very, I mean, can we think of a systematic procedure for implementing any Boolean expression using NAND alone, maybe using minimum number of NAND. Now it is interesting. So if you go for the standard realization, means all AND operation you are implementing using 2 NAND gate, all OR operation you are implementing using 3 NAND gate, like that if you keep on doing, you can implement, but it will be a very complex circuit. So now can I do it using minimum number of NAND gates? Typically this is another type of question that you can expect. How many minimum number of, so this here the realization I am interested is, I want to know what is the minimum number of NAND gates for a Boolean function. Okay, so the thing is that what you have to do is the given Boolean function, right? Boolean function, you convert to what? The minimum SOP form. And you know how to convert any given Boolean expression or function to a minimum SOP. Use K-map and do simplification, whatever it is. So now once you have this minimum SOP, I am going to tell you a systematic way by which you can implement the equivalent NAND gate realizations. So that's all. So something like this. Suppose I have this as the minimum SOP expression of a given Boolean algebraic expression. So whatever it is, you use K-map and all, you come up with this kind of a notation right now. From this point you can go ahead. So what you have to do is, You know, this is now, it is just like so let me write here. See, this is my function. I have a function. The function is something of the form AB plus CD. Now, you know, this is something you can visualize as a particular input, say x1. This is another input x2. So, two inputs are actually, I am doing this XOR operation. I am doing this OR operation. Now, you know how to implement this OR operation using NAND. So, keep that in mind. So, OR operation using NAND. Hope you remember, OR operation using NAND. 3 NAND gates you applied, right? So, what you done is the first input you complemented. Right, the first input you complemented, the second input also you complemented. Now, both the complemented inputs you given to the third NAND gate. The first NAND gate complement the first inputs, second NAND input applied parallelly complemented the second input. Hope you remember this, right? And the third NAND gate is going to give you the complement of this, something like this. So, keep this in mind. So, this is the idea. So, the implementation of what I was trying to say you is this this part. See, the implementation of any something like this, a plus b is implemented like this is the first NAND gate, this is the second NAND gate, right? So, that is giving you the first input complement, second input complement, and the third NAND gate is going to give you the final answer, the a plus b. In a similar way here, see, yeah, the first input complemented by the first NAND gate, second input complemented second NAND gate, and finally these two are further applied to a third NAND gate, and this is going to give us, this is nothing but this is equivalent to x1 plus x2. So, now you should know how to write this from x1 plus x2. So, that is the whole things, that is the only thing you have to remember. So, from this, you know, this is equivalent to x1 plus x2. So, now given this x1 plus x2, can you write like this? This x1 plus x2 is equivalent to x1 complement dot x2 complement, the whole complement. Because why I am writing like this? This x1 complement I can implement using a NAND, this I can implement using a NAND, and finally this also I can implement using a NAND. So, 3 NAND gates are enough. Same way, now instead of a single input I am having some product term like AB. So, okay, fine. So, just write like this, the first input the complement, x1 complement, like that AB complement, say dot, right, in between nothing is written means dot. Then the second input complement, x2 complement, right, a CD complement, and finally the whole complement. So, AB plus CD is nothing, is equivalent to AB complement dot CD complement, the whole complement, right, fine. Now, this is nothing but AB plus CD. Now, you can implement it, right. So, how to, instead of a single input, I just have a 2 variable product term, fine. I can just using a single NAND gate I can do this, right. So, what I have to do is this A and B, use an AND gate. This is the first AND gate. This is going to give me A, B, the whole complement. And similarly, C and D, use a second AND gate, right. So, just like x2 complement, this is going to give me the CD complement. And finally, the third AND gate is going to give me what? A, B, the first input dot the second input, right, the whole complement, and this is equivalent to AB plus CD. So, that is what I want to implement, right. So, this is the logic. So, now you find it easy because just two something like A, B, C, D, 2 product terms are involved. Now, same thing you can implement using means if there are 3 product terms, then you similar way you try using a 3 input NAND gate. So, that is the idea. In the last level you have to use a 3 input NAND gate. Now, how to implement 3 input NAND gate using 2 input NAND gate, methods are there. Maybe I am giving all those things for your additional reading. So, for the time being we can wind up this second module because we taken a lot of time for many concepts. Maybe in future time, if time allows, I may create more videos on it. Actually, you have to spend some more time for second module. So, just like this NAND gate itself, you try to see, let me just give you some of the things for your own personal reading and understanding, right. So, we can go through something like the implementation of XOR gate. Try this XOR gate using NAND. So, everywhere I just want the best implementation. So, I was asking you like the minimum number of NAND gates used to implement XOR gate, or let me write it clearly like minimum number of NAND gates required to realize, try this XOR as well as XNOR. Similarly, try this the same one you try for minimum number of NAND gates or NOR gates. So both you try. Okay, fine. So that is something you can do, and just take any maybe something like implementation of a, along with this. So here we are thinking about the 2 input and AND gate or a NOR gate. Okay, so by default an AND gate, I mean 2 input. Now you can try to the realization of a 3 input NAND gate also using this 2 inputs, so that you will get an idea, right? So in general, try to practice more questions on realization or implementation realization using NAND gates as well as NOR gate. Now you may be wondering how to implement any function using NOR gate. Now the idea is, for NAND gate we used that SOP, right, sum of product expression, minimum SOP. From that you right now you understood how that straightforward realization can be done. Similarly here we can depend this POS expression for the implementation of any expression using NOR gate. Yeah, that about it. So hope you get a brief understanding of this implementation. Now see, we are going to the third module, where you will see lots of example for the realization of any practical circuits, particularly the adders, subtractors, multiplexers, etc., using this gates and all. And that time you will get a very broad view of this, right? And okay, so by that time this implementation part will be clear for you. Now you can second module you can spend more time on realization of more and more examples using this NAND as well as NOR gate. Yeah, so that about it. So you can see as a conclusion, this NAND as well as NOR gates alone, both this. So what are all the fundamental gates? Fundamental gates, sometimes we call it as the fundamental sets of gates, something like that. So one fundamental gate is this, fundamental gate, something like this AND gate, or fundamental sets of gates, something like AND gate, OR gate and NOT gate. Together you can implement. So fundamental gates means using which you should be able to implement any other Boolean algebraic expression. Now another one is just this NAND gate alone. So that is what we seen so far. Okay, now the third set is something containing this NOR gate alone. But is it enough? I mean, is this set is stopping here? So can we think of some other combination of gates using which you can implement all other, maybe a single gate or more than one gate, okay, using which you can try to implement all the Boolean expressions. Okay, you can think like that. Actually such combinations are there, you can try to explore them also. Okay, so you can take this also as an exercise for you. So please be sincere and try to do all this, and if somebody is doing sincerely, you can approach me, like your doubts and all, I will try to clarify. Okay, yeah, thanks for watching.